much for introducing me. Us. Like I said, I'm Dennis and this is Redha. This work was done in collaboration by all the people whose names you can see on the screen. This is thus a collaboration between the TU Munich, TU Delft, University of Edinburgh, and the University of St. Andrews. So let me start off by explaining the problem. Previously, x86 CPUs dominated the market in many different domains. Yet in several domains, we now see ARM emerge. So for instance, in personal computers with Apple's recent introduction of the M1 and M2 chips, or as evidenced by major cloud providers offering ARM-based instances. So one question one can ask here is, what does this mean for the legacy x86 applications? So whenever you have the source code available and it has no x86 specific assembly codes, then sort of recompiling it and running on ARM should be possible, or maybe as we saw before, not always, but sometimes maybe it is. But there are even worse cases where this is altogether impossible. So if you have only pre-built x86 binaries, or your code base contains x86 assembly code, so either your application itself, or maybe some of its dependencies do. Or maybe you've only tested your application for x86. In these cases, we argue that binary translation is the way to go. So the idea is that we take an x86 binary program and we try to run it on ARM. Of course, when translating such a program, these translated binaries must have the same behavior on the target architecture, which is ARM, as they did on the source architecture, which is x86. So one question you can ask here then is, what about the architectural differences between these source and target architectures? So in particular, we look at the weak memory models, which specify the reordering rules for the memory accesses. Note in particular that ARM has a weaker model than x86. So we've already seen, I think, similar examples in the session before, but I will go briefly through it again. So here we see two threads which do memory operations. So we start off with two memory locations, separate memory locations containing the value 0. And then on the left thread, we write the value 1 first to x and then to y. In the second thread, we have a condition and an assertion. So the main idea here is that on x86, this assert always succeeds. So either, the branch is not taken, or whenever the branch is taken, the assert succeeds. But on ARM, we can see that this particular assertion can actually fail, which happens whenever the instructions on the first CPU, or on the first thread, are reordered or executed out of order. So the issue here is that if we were to naively translate this program from x86 to ARM, suddenly we introduce a new behavior, which for this particular example is actually, incorrect or like undesired, basically. And we want to avoid these cases. So a main challenge we have to overcome is that we need to enforce the source memory model on the target architecture. And to do this, we can indeed place memory fences next to the memory operations. So again, we've seen this before, but the idea of a fence is indeed that you cannot reorder instructions across fences, and so they cannot be reordered by the CPU. QEMU, which is a state-of-the-art binary translator, does this to enforce the x86 memory model on ARM by inserting strong fences before every memory operation. In particular, note that it places a full fence before a store operation, which is a relatively expensive fence, and we have also seen this in our experiments. So what we observe is that for the Parsec and Phoenix benchmark suites, 48% of the execution time is spent executing these memory fences. So we prefer to have fewer of them. But even at this really rather high performance cost, we see that even QEMU is not actually correct in all cases. So in particular, we found correctness bugs in QEMU for its atomic operations. So the main thing we looked into is, and we tried to solve, is that how can we maximize the performance of binary translation while ensuring the execution correctness? And Redha will now explain our solution.
So we introduced Risotto, a dynamic binary translator for weak memory model architectures. And so the main idea is that we base our design on QEMU again and its intermediate representation, TCG-IR. So we work at the user level translation. So the idea is that you take your guessed binary, so x86 in this case, you feed it to QEMU that will translate x86 instruction to this TCG intermediate representation, and then from this representation to ARM and execute the code. And we only emulate the user mode level code, while every time there a system call happens, there will be a call to the host kernel on the machine. We have two main goals with Risotto. The first one is correctness, where we'll provide precise memory mappings to do the translation and enforce the x86 memory model with formal correctness proofs. And the second goal is performance, where we'll try to generate more optimized code and maximize the use of native code instead of translating code. So first, let's focus on correctness. And so to this end, we propose these precise memory mappings to enforce the x86 memory model. And what we mean by precise is that every fence that we insert is necessary and sufficient, which means that if we had a weaker fence, we wouldn't have the x86 behavior. And if we had a stronger fence, it would just be stronger for no good reason and just hurt the performance. So here you can see again the translation that QEMU does. And we switch this a bit by having some weaker fences and switching a bit the order. I'm not going to go into too much details here for the presentation, but you can check out the paper for more details. The main thing you must take from this is that these can be verified, and these are more efficient because they allow more reorderings at the CPU level, and they also allow us to do some optimizations such as fence merging. So with these mappings, we formally verify their correctness with the Agda theorem prover. And the idea is basically that we take an x86 formal model of the x86 memory model. And same thing for the ARM memory model. And we also introduce a similar model for the TCG intermediate representation. And we show that all the transformation with the fences that we have still carry on the x86 memory model through all this translation process. However, during this formalification step, we also noticed that there was a slight issue with the official ARM memory model that I'm going to show a bit. So basically, when we're working on the CASAL instruction, which is the compare and swap acquire release, so the instruction does an atomic compare and swap. And as the acquire release means, that should act as a full fence. However, when we run our proofs, we showed that actually the official ARM memory model does not enforce this full fence here. So we had to fix the model for our work and submitted the issue to the ARM developers that actually fixed this a few months back. Now let's go to the performance side, and I'm not going to go through the optimized code generation, but just for the maximizing the native code use with a trick that we have with dynamic libraries. So why do we want to maximize the native code usage? So basically, native binaries, so binaries that are compiled from source code to assembly, are usually faster than translated binaries because compilers are way more powerful at doing full optimizations on the program than what binary translator can do. And so we think that, okay, if this is true, then we can just maximize the code that was directly compiled for the target architecture, and this would give us a performance boost. And the idea here is that most dynamic binary translator usually we'll have the host kernel running with host instructions, so in our case ARM, and everything aside from that will be translated. So the binary of the program and the libraries that it uses will be x86 programs translated to ARM. What we want to do with Risotto is to move this boundary and include the libraries in this native host binary base that does not need to be translated and will be more efficient. And to do this, we introduce a dynamic host library linker that will basically detect the calls to shared library functions in the program. And whenever such a call is detected, instead of calling the x86 version and translating it, we will patch the target drop address and evoke the native host library instead. This way, we can just run native code instead of translating it. And with this, we hope to achieve the same performance as native libraries directly. Now, let's talk a bit about the performance evaluation. So we ask ourselves two main questions. First of all, do Risotto mappings outperform QEMU mappings? And to check that, we compare Risotto with QEMU, which, should I recall, is incorrect. And we check on the Parsec and Phoenix benchmark suites. And the second question is, does our host library linker achieve native performance for shared libraries? Again, we compare ourselves with QEMU, and we benchmark this with some benchmarks that exercise shared libraries a lot. So for memory mappings first, we run Risotto against QEMU on the Parsec and Phoenix benchmarks, and here is the runtime of Risotto with regards to QEMU, so 100% the red line is QEMU, and the lower the value, the better. And what we can see is that overall, we're either as fast as QEMU or faster than QEMU, and on average, we get a 6.7%, we're faster, 6.7% faster than QEMU, and this is due to the fact that the CPU can do more reorderings than what QEMU allows with its fences, and also we have some optimizations where we can merge fences that QEMU could not do before. As for the dynamic host library linker, we use the OpenSSL shared library and the SQLite split test to check. So again, we compare Risotto and also native execution in orange. And this time, be careful because we switch the order. This is the speed up with regards to QEMU and not the overhead. So higher is better. And again, we see that Risotto basically matches the speed of native execution. So whether you use a translated binary with Risotto or a native binary that uses these shared libraries, it's as fast. Yeah. So to summarize, we propose Risotto, which is a dynamic binary translator for weak memory model architectures that provides correct enforcement of the x86 binary model on ARM hosts. And we do this by giving a formal model of QEMU's interpreted representation, TCG, precise memory mappings to do this translation from x86 to ARM via TCG, and the proof of correctness of all these transformations. And we also fix a bug in the official ARM memory model. And for the second goal, that is performance, we show that we can improve the performance of the translation just by having these new precise mappings, and also by using as much native host code as possible with this shared library linker. Thank you for your attention. You can check out the paper here, and if you want to try it out and check, we have everything available. Thank you.